And welcome to Climate Chat. I am your host, Dan Miller. And today our special guest is Brendan Clark, who is a Cornell atmospheric scientist studying the impacts of climate change on agriculture. And we're going to learn a lot of things, and I bet you're going to learn some things you've never heard about before. And Brendan, welcome to Climate Chat. Great to have you here. And perhaps
Yeah,
we could start off with you telling us a little bit about your background.
yeah, great. Yeah, thanks for inviting me. This is great to be here. So I'm a researcher at Cornell University. I work with
My alma
Professor.
mater, by the way, I should just
Oh
throw
yeah,
that
I
in.
didn't know that. Nice. Yeah, I work with mainly with Professor Daniele Visioni, who I think you've had on the show, and also with Doug McMartin, who also I think has been on the show. I'm a global modeler, so I use numerical models of the globe, similar to a climate model, but looking at vegetation impacts, so models of the land surface. And I mainly study I study impacts from climate change on things like trees and agriculture, but also I focus a lot on geoengineering, things like stratospheric aerosol injection, which we can talk about. And yeah, I got my PhD about a year and a half ago from Rutgers University, where I also studied stratospheric aerosol injection impacts on agriculture, and I also had a lot of exposure to things like nuclear winter impacts on vegetation, which the title of this is Dimming the Sun, What Would Happen? I mean, that's like an extreme dimming the sun.
Right.
That's because that's what my advisors worked on a lot too at Rutgers. So I had a lot of experience with that as well, although my research was mostly geoengineering. But yeah, it's pretty much a big picture what I work on. Yeah.
So actually, that's a good point to start off on. So I did use dimming the sun
Yeah.
because it's just something that people who don't pay attention to climate change can maybe understand what it means.
Yeah,
If
it
I
makes sense.
say
Yeah.
SRM, they won't know what it is.
Yeah.
But when we talk about sunlight reflection methods, ways of cooling the Earth to prevent the worst impacts of global warming, we're talking about dimming the sun a little bit
A little bit.
compared to nuclear winter. So maybe you could start off by telling us how much, when you're doing your studies of quote dimming the sun, how much dimming is there actually?
In a typical simulation in like a climate model, I mean, it depends a lot on like the scenario, but something like, a medium emissions scenario by the end of the century, if you want to maintain like 1.5 degrees above pre-industrial, something like that, you might be dimming the sun by like, at most 2 or 3%. So it's a modest amount, but it still would have, pretty important implications. But yeah, nuclear winter is not really geoengineering. Geoengineering is like you're intentionally trying to control the climate. That's just
Mhm.
nuclear winter is a byproduct of an all-out nuclear war. All this smoke from burning cities going up into the atmosphere and blocking out the sun. That might be more like, 20% or something. It can be something crazy. That again depends on how many nukes there are and stuff like that. But that's
Sure.
like just a ton of sunlight blocking, which is really, really bad. Yeah, you don't. That would be way too much, and that would be very devastating for agriculture and stuff like that.
I never heard the amount nuclear winter was. That's interesting right
That
there.
would be like, US versus Russia all out war, but
Yeah.
there's other places with nukes like India and Pakistan, and they could presumably, go after each other, and that might be smaller because they have less nukes, but so it gets into that kind of stuff, size of arsenals and stuff.
So before we get into your work looking at the impact of SRM on agriculture, you've also your one of your most recent papers. Let me see if I can pull it up here. With There we go. One of your most recent papers is called "Land Models Likely Underestimate the Impact of Future Atmospheric Dryness on European Tree Growth." And so, what you're talking about here is about how we think, that trees will capture carbon and whatever, but if they don't grow as much as we thought they will, that won't happen. So maybe you could give us an overview of what this paper is all about.
Yeah, so like I said, I mostly work on geoengineering, and this idea originally came up like 4 years ago at a geoengineering conference, talking with ecologists, like what would happen to trees? Can we use observational data to understand that? But the more I thought about it, and I went to a bunch of different, I go to conferences every year, like the American Geophysical Union, which is this huge conference, like 20,000 scientists. And when I went, I would go a lot more to these sessions where it's, people who study trees, looking at how tree growth measurements are changing. And I was realizing that there's all these different people going out into the field and basically measuring tree growth. So you can go out and wrap a band around a tree. It's called a dendrometer, and basically measure how much is growing, very, very fine time scales and fine amounts. And then they compare that to, you can also measure photosynthesis. There's things like eddy covariance, flux tower measurements. It's pretty complicated, but basically measuring how much CO2 is going in on the leaf. And so they're comparing photosynthesis to actual growth, and they're finding that the two things are completely decoupled a lot of the time. And if you're a land modeler like me, these land models that we use to try to see, okay, how much carbon is the land going to absorb in the future under climate change? These models assume that photosynthesis, it basically directly equals growth. If a tree is going through photosynthesis, then it's growing and it's storing carbon. But all of these observational studies it's really a recent thing in the ecology literature. There's all these studies still coming out that are saying that actually a tree can be photosynthesizing but not growing, which is like, if you're a land modeler, this is a really big problem because that's the assumption that these models are basically built on. And the reason is, a photosynthesis can drive tree growth, but also if the air gets too dry or the soil gets too dry. So I focused here on the air being dry. That's kind of the main driver of tree growth, is what these studies are finding. What can happen is that, yeah, it can slow down photosynthesis, but it can also just, things like the cells of the tree can dry up and shrivel up, and so they can't go through cell division. They can't allocate any carbon from photosynthesis into growth. So they could be going through photosynthesis, but the air is so dry that they can't actually store that carbon anywhere. And so,
Yeah.
you're going to ask something, yeah.
Yeah, well, so the very first YouTube live version of Climate Chat, which was several years ago, after we moved from Clubhouse to YouTube, was on, I think the title was The World Stopped Greening 20 Years Ago. And it was all about vapor pressure deficit, something I hadn't heard about before I did that show. And it turns out to be a rather important thing, and it's involved in your paper as well. But unlike that paper that I was covering back then, yours is actually different. And I thought that was really interesting. So maybe you could start off and maybe explaining in sort of the easiest way possible, what is vapor pressure deficit? Yeah. How does climate change or global warming impact that? And how does vapor pressure deficit impact plant growth?
So yeah, it's a fancy term. I mean, basically what it is how dry the air is and how hot it is. So it's a function of both temperature and humidity. And so when vapor pressure deficit is high, it means the temperature is high and also the air is really dry, so the humidity is really low. And so this is really, really damaging to plants. Plants do not like it when it's too hot and too dry. Those two things combined put a lot of stress on plants, which is interestingly kind of the opposite of humans. For humans, if it's really hot and really humid, that's what's damaging. Your body can't regulate its temperature as well. But for plants, it's the opposite. Really hot and dry, that's what's really bad. And so, yeah, so that damages photosynthesis, but there's all these new studies coming out that's actually really important, and it can damage and hamper growth a lot more quickly than it damages photosynthesis. So, yeah.
But the kind that the study from years ago was talking, I mean, I don't even remember the exact mechanism, which was different than your study, which talks about the woody growth and things. So, climate deniers like to say, oh, CO2 is plant food and the world is greening because of climate change. And that's a great thing. And it's really not as true as they, I mean, yeah, CO2 is plant food. That's fine. And
yeah,
but there really are a lot of other factors. And so as global warming increases, vapor pressure deficit is increasing as well, right? And that, is it true that we've stopped greening, as far as you know, in terms of overall effect of extra CO2 versus vapor pressure deficit?
So I think there's some, limited evidence from things like satellites that, maybe the world isn't greening as much as we thought it was. And so, yeah, so these land models that I use, if you run them into the future with climate change and you increase CO2, a lot of them are just like, more CO2 is great no matter what, which, there's a lot of evidence that suggests that's probably not true. You can't just dump CO2 forever into the atmosphere and the plant's going to keep growing. At a certain point, things like heat stress are going to take over. But a lot of the models don't show that. And I think that this paper looking at, even though maybe photosynthesis, if CO2 keeps going up, maybe it does tend to go up and up and up, but actual plant responses to that, I think, is a lot more complicated than just photosynthesis. I mean, there's this, microbiology going on within the cells where they can shrivel up and they can't, the carbon can't be stored, that the models aren't including. So yeah, so there's a lot of evidence to show that these land models, overestimate the strength of the carbon sink compared to current day. And we don't know for sure why that is. This, is maybe one reason, but there's tons of reasons why that could be.
So overall, in your paper, so you found that vapor pressure deficit has impacted growth, at least so when it comes to European trees. I guess that's where you focused.
I
What
focus
would
on
you
that
say
'cause,
the overall effect was? Like, in other words, how much less are trees taking up carbon than was assumed in the models you say that aren't accurate?
So the way that I did it was pretty simplistic, where I just tried to correct the output from the model to match the observations from these dendrometers. And what it did was it ended up reducing the carbon storage in the future by as much as 30% in some places
Wow.
that are drying the most. So I will stress that the way I did it was simplified. What you'd actually want to do is go into these models and try to implement even a pretty simple way of actually representing these processes that can limit growth besides photosynthesis. And I think there's ways to do that I haven't done yet, but I think that's really the next step to be a lot more, to increase the confidence in those corrections that I was doing basically. But it indicates that this could be pretty important. Yeah.
Well, a third less carbon uptake in trees is a pretty
Yeah.
big thing. Yeah.
Yeah.
Okay.
I think it's going to be important to try to include these mechanisms within these models in some way or another. Yeah.
So besides this particular paper, you've been quite prolific. Let's like pop up some other, let's see, some other papers here. Maize yield changes under sulfate aerosol climate intervention using 3 global gridded crop models. That's kind of a mouthful.
Yeah.
And you have another one here, which I was reading the abstract. So stratospheric aerosol climate intervention could reduce crop nutritional value. And by the way, and just so everyone knows, I have your Google Scholar link in the video description.
Okay.
So anyone can get to all of your papers.
Yeah, go check them out. Yeah.
Yeah. And tell us what, again, you mentioned it briefly. What was the title of your PhD thesis, which is also accessible here?
I think if you scroll down, it's there. It's like global agriculture.
What year was it?
It should be up towards the top. Oh yeah, up a little bit more. Yeah, there you go. Stratospheric sulfate aerosol climate intervention implications for
Oh
global
yeah, it's just you,
agriculture.
right? Yeah, this is.
Yes, that's it.
And if you want, so this is actually your thesis. So it's not a
and that's
not a regular paper,
basically,
but it's like a book. You can read a whole book on it.
yeah, a thesis. I mean, that's basically 3 of my papers kind of stapled together. That's basically what a dissertation is.
Yeah.
But yeah.
Okay, so let's talk about this now. So we have global warming. The climate is changing. We're not reducing our emissions like we need to. And temperatures are rising. We're at 1.5 degrees now, on track for 2 degrees, maybe in 2037 timeframe.
Yeah.
And 3 degrees in the 2050 to 2060, maybe a little bit more timeframe. That's really bad. So many people are proposing to do what's called sunlight reflection methods. Solar radiation management is another term, SRM.
Yeah.
And also it's called solar geoengineering. And I'm just trying to get the words out.
There's a million. Yeah, there's so many. Yeah.
And there's a particular type of SRM where we put sulfur in the stratosphere, and that's SAI, sulfur aerosol injection. It also has another version.
Stratospheric aerosol injection. Yeah.
Stratospheric aerosol injection. Right. I'm sorry. That's the one. Yeah. So that's the one you're focused on.
That's what I research. Yeah.
Yeah. So
Yeah.
let me switch away from the paper for a second here. We have to go here. And there. Okay. So, all right. So that kind of sets the stage. Now we're going to start talking about how SRM or SAI impacts agriculture. So, and you've done lots of different things. You've looked at a lot of different aspects. Maybe you could just start off telling us what are some of the positive impacts of doing SAI, and what are some of the negative impacts on plant growth for doing SAI? Like what's kind of a range of the things you have to consider?
Yeah. So, sorry, the connection's a little bad. I don't know if it's me or you, but I dropped out for a second. Can you still
Yeah, I
hear
saw
me?
that, but you're back. So
Okay, good. Okay. Yeah, so with SAI, so you're increasing CO2 like we said. That's plant food basically. So if you increase CO2, you don't touch CO2 and you keep it high, and you reduce heat stress, you know, to first order, you would think that's probably pretty good for plants. Um, and generally, that's kind of what you find, especially in the modeling literature. You're keeping CO2 high, you're reducing heat stress, assuming you don't totally screw things up. I mean, there's ways to totally screw things up with stratospheric aerosol injection. If you deploy too much in one hemisphere, you could shift the intertropical convergence zone, which is this band of precipitation along the equator. And billions of people rely on that for rain-fed agriculture. If you screw that up, that's a big problem.
right.
And there's things like termination shock, which people like to point to a lot. You're doing this SAI over long periods of time. You stop doing it after a couple of years, all the aerosols fall out due to gravity. You get this spike in warming that would be really, really bad.
Right.
But assuming those things don't happen, you're reducing heat stress, you're keeping CO2 high, you might be modifying precipitation a bit. But in my opinion, the most important thing you're doing is you're modifying radiation pretty substantially. You're going to be changing the way radiation is coming to the surface in a way that's a bit unprecedented, besides things like volcanic eruptions.
Hmm.
So there's really two opposing forces that are relevant for plants. And one is that you're reflecting sunlight, that's the cooling you're getting. But because of that, you're getting less total radiation reaching the surface. So that's less light available to do photosynthesis, which you would think would be bad. But at the same time, you're doing that. These aerosols you're putting in the stratosphere, they're backscattering light, but they're also scattering light forward and scattering light in all directions. And so that makes the photons sort of bounce around in different directions rather than just straight down from the sun. And that's called diffuse light. And diffuse light is actually pretty good for plants. And so the impacts to plants from geoengineering, like stratospheric aerosol injection, it depends a lot on, well, a lot of things. But one of the big things is, what kind of vegetation are you interested in? Mainly canopy structure. So when you think about a forest, it has a dense, thick canopy. When you go out and walk in the forest, you look around, it's mostly shade on the ground. And so that shade is not really getting direct sunlight. And so when you increase the amount of diffuse light, these photons that are bouncing around, they can sort of enter the canopy from different angles and get to the ground. And so light up these plants that were otherwise shaded. So that's actually would be a really beneficial thing to forests for the most part. And then so for agriculture, farmers are, they're shorter obviously, and farmers are purposefully spacing out plants when they grow them to maximize light interception. So there's not as much shade. If you would go out into like a cornfield relative to a forest, there's not as much shade. They're getting a lot of direct sunlight. And so for them, things like reducing total radiation can be really important too. So I'll say, this is still a really big uncertainty and depends on a lot of things. I mean, but I will say that, yeah, the radiation effect is one thing. You're getting the heat stress reduction. The net effect of doing this geoengineering impacts on plants. The odds of the net effect being negative globally for forests is pretty much zero. It's almost certainly going to be a good thing for forests because of that canopy structure I said. There's no evidence to indicate from observations like volcanic eruptions like Pinatubo or from modeling studies that forests would be damaged overall from geoengineering.
Would not be.
Would not be damaged. I mean, you're reducing heat stress, you're keeping the CO2 high, you're increasing the fraction of diffuse light. Like I said, you're only reducing total radiation by a couple of percent. That's not enough to be really detrimental. And the tops of canopies in forests are already really light saturated. They get tons of sunlight.
Okay, so that's
Yeah.
good. So overall, so far that's far. So when people, I mean, that's something that I guess many people worry about when they just hear about SAI. They just what? You're going to block the sun, and oh my God! And so you're saying actually overall it's actually beneficial.
For forests,
forests.
yeah, it would probably be beneficial. For agriculture, it's a bit different. Like I said, they have a different canopy structure, and there is some evidence. Like if you use, the best analog we have for SAI is volcanic eruptions. So there was one study that looked at Pinatubo. How did the aerosols after Pinatubo impact plants? And this study, it was published a few years ago, published in Nature, they found that the radiation impact from SAI was very negative for agriculture, and it counteracted the positive effects of cooling temperatures. So the net effect was negligible, and I would say that's more of like a worst case scenario. Pinatubo, you know, the amount of diffuse light and the amount of total radiation loss you get, it depends a lot actually on things like aerosol microphysics. So what is the size of the aerosols you're getting from doing this injection? Pinatubo had slightly larger aerosols, so maybe, I don't know if this will mean anything to people, but like, half a micron, very, really small, but they're actually pretty large compared to the modeling studies that we do. And so what ends up happening is because they're larger, you actually end up getting slightly less diffuse radiation for the same amount of total radiation reduction. And then when we go into, we use climate models and we try to just simulate SAI. A lot of the times we use these smaller aerosols, you get more diffuse light, you get more scattering for the same amount of total radiation loss. So, in a way, using Pinatubo might not be necessarily a good analog for SAI, but also at the same time, I would argue we have no idea what the size of these aerosols are going to be when we do this. You're talking about, flying airplanes up into the stratosphere, dumping sulfur dioxide out of the back. There's plume dynamics, there's, coagulation, these aerosol microphysics going on. And it's really hard to know what size aerosol you're going to get from doing that. But the size is actually really important for determining the impacts you get to vegetation. If you have slightly smaller aerosols, you get more diffuse light, that tends to counteract the negative effects of loss of total radiation. If the aerosols get slightly too big, maybe you do the injection and they coagulate too much, they get a little too big, all of a sudden the radiation impacts could become damaging. And so at least after Pinatubo, that was, the aerosols from that tended to be pretty damaging for agriculture. And the net effect was still, negligible. You still have cooling, you still have benefits from that. So in terms of the evidence we have from modeling and from observations and analogs, the worst case scenario for agriculture is probably a wash, is probably negligible. Like, you're probably not going to be reducing yields globally by some amount that's damaging. It's probably either negligible or a positive effect, depending on things like the aerosols you get, the size of them, the radiation impacts you get. But radiation is really the big thing that would be determining the magnitude of the response you're going to get.
So actually, I guess an important question is, in your studies, what do you assume the non-SRM temperature is? Are you doing a 2-degree world, a 3-degree world, a 4-degree world? I mean, I think agriculture is output is very, very different under those different conditions.
Yeah, so I mean, that's a really good point. So your impact studies for SAI, it's always going to depend on what is your background climate change scenario. Is it a high emission scenario with lots of CO2? Is it a medium emission scenario with less CO2 and less warming? How much SAI are you doing? Do you want to cool to 2 degrees above pre-industrial? Do you want to maintain 1.5? You could go down to pre-industrial if you wanted. Would that be better? And so the impacts you get are going to vary. And also, things like what latitude do you inject at? That's really important too. And
but it's also the time. It's how long you wait. I mean, you wait 10 years, you're at 2. You wait 30 years, you're at 3. So
yeah, and then if you're at 3 and all of a sudden you say, I want to cool back to 1.5, you might get rapid cooling, and maybe that could be damaging too. So there's things like that as well.
Right.
Yeah. And then also,
So what is assumed in your papers? Though? What's the basic? Because you're coming up with these numbers, so you have to be making some assumptions.
Yeah. So I think my recent papers usually use like a medium emission scenario. If people are familiar with like climate modeling, it's the SSP2 4.5. So it's 4.5 watts per meter squared of extra radiative forcing by the end of the century. And then usually the scenarios I use maintain 1.5 degrees above pre-industrial levels, just to follow the Paris Climate Agreement. That's just kind of a politically relevant number we have. That's what these modeling studies tend to use. But yeah,
well, does that? What I don't recall what that implies in terms of global temperature at the end of the century, though. Is that about a 3-degree scenario or something?
It depends on the climate model you use. So climate models have different climate sensitivities, different amounts of warming for the same amount of CO2. I think in general, SSP2 4.5, you might get 2.5 degrees of warming, maybe 3 degrees of warming by the end of the century. And so with SAI, you're offsetting about a degree and a half of global
Okay.
average warming. Yeah.
Sounds a little optimistic. We do a lot of, we
Yeah.
cover Jim Hansen's work here. Leon Simon's my
Okay.
co-host. He's
Yeah.
not available
He
today,
would
but
say, yeah.
he says
Yeah.
4.5 degree climate sensitivities. And he says he can prove that 4 different ways. So
Yeah, I'm not I'm not going to speak on that. I know there are people that disagree with Jim Hansen, but
oh yeah, sure. Yeah.
yeah, but certainly it's certainly possible that SSP 245 is a bit optimistic. Yeah.
So the other question I have for you is that we're talking about this purposeful SAI where we're going to put, I don't know, on the order of 10 million tons of sulfur, maybe a little bit more, in the stratosphere using airplanes. But we're currently doing SAI on a massive scale. We're putting 70 million tons in the lower atmosphere, where I assume it also diffuses light and things like that, I guess. Has anyone, or you or anyone, done studies on how accidental SRM is impacting agriculture? Like, is it helping, hurting, like what we're doing right now?
There are people that study that. I think it's pretty hard to do. For pollution, it's pretty hard because it's not like a year-round perturbation. Like, it's going to go up and down depending on, the time of year. It's probably going to depend a ton on where you are, how much pollution
Of
there
course.
is.
Yeah.
And so I think in general, studies find that more diffuse light is beneficial. And it's very nonlinear though. So, diffuse light up to a point is beneficial, and then the loss of total you get can start to become negative. And so, where it peaks on that amount of diffuse light, where that curve peaks, depends a ton on where you are, what kind of plant you're interested in, what kind of crop. And so, it's really hard to sort of synthesize that and apply it to an SAI scenario. But there's very few people that use observations to inform SAI impact scenarios. It's mostly, like pollution, what does that do? But the results tend to vary. There's also things like clouds scatter light. They modify the amount of diffuse radiation and total radiation. There's wildfire events that do similar stuff.
Right.
So you can use those as kind of analogs to try to inform your modeling and stuff. But there's been I think overall this field has not been utilizing those as well as we could. And I think that's one of the next steps in research is better utilizing observations of stuff like this that naturally modify the amount of diffuse and total radiation. Yeah.
I guess if we had a really big volcano, that would help as well. We could.
That's the best analog. And like, Pinatubo was really the last big volcano that put sulfate aerosols in the stratosphere to have a really meaningful impact. And, that was 35 years ago. I mean, our observations from them on plants was really, really not very good. So we have very minimal observations from them. If there was a big volcanic eruption that happened, like, I mean, hopefully no one died, but that would really actually be really helpful for informing.
It'd also cool the earth for a while.
Yeah, it would cool the earth.
And people might like it. They go, wow, that was nice. 2 years, man. It was like so much better. And then it comes back. And then people say, can we do that again? And yes,
I mean,
the answer is yes, we can.
That's what happened after Pinatubo. I mean, it cooled by, a degree Celsius global average. And, there's tons of evidence to indicate that the photosynthesis rate around the world went up by quite a bit after Pinatubo.
Really?
Yeah,
wow.
There are some studies that have looked at that. Yeah, there's like I said, there's minimal evidence, but there was one study that was directly observing a forest growth at the Harvard forest site. And they found that after Pinatubo, that the photosynthesis of that forest site went up by like 23% just due to the radiation changes alone, not even accounting for temperature and stuff. They found that radiation was the most important thing, and it benefited the forest there by a huge amount. So there is evidence from Pinatubo to suggest that natural vegetation would like this for forests. And then, like I said, for agriculture, there's some evidence to indicate it might be slightly more damaging, but yeah.
Well, so you've done a lot of different work. You've looked at different crops and different regions. So maybe you can just tell us some of your conclusions. Like I saw your paper on protein decreasing. You mentioned that corn and rice. You look at different regions, and some are good and some are bad. Maybe you can just tell us, like, if we actually did SAI, who do you think the winners would be in terms of agriculture? Who the winners would be and who would be the losers?
So in terms of yield, so that's what most people focus on, is how much crop are you going to have. In terms of yield, it's pretty clear, like for the modeling studies across the board, that the biggest benefits you'll get are lower latitudes, places in Africa, places that are going to have tons of heat stress under climate change. And it's also pretty universal across the board that you're going to get reductions to yield at really high latitudes. So places like Canada and Russia, that
Hmm.
where warming for plants, at least, might actually be kind of a good thing because it's so cold there already. You might be extending the growing season. And so for those places, it's totally possible that SAI could be damaging. And so I think that deserves more research. And it's also, a potential source of conflict in my mind. The geopolitics of that could potentially get messy. I mean, my advisor from a PhD, Alan Robach, he used to always say, when people asked him, what's the worst thing that could happen from doing geoengineering? He would say, well, nuclear war.
Right.
If you have Russia saying, what's going on, we like the warming, all of a sudden, our yields are going down, stop doing this, US or whoever. And they say no, it's like, well, you could have a war from that. You're arguing over the thermostat of the planet, basically. So the geopolitics of this, is the biggest thing that would be so hard to get around. I mean, people might say, oh, well, if people, are being damaged by geoengineering, you could just compensate them. But, attributing, things to the geoengineering rather than just natural climate variability would actually be really hard to do. I don't think we have a great way of doing that, even for climate change. And it's, like people could say, you start doing geoengineering, even a small amount that's not barely impacting climate. The next time there's a hurricane or a tornado, people are gonna be like, it's you geoengineers, like you better stop doing this. Like, but it's like, it probably wasn't the geoengineering, but
Right.
so,
But even
yeah,
so, if we don't do geoengineering, then you have wars over, unlivable countries and people
yes,
migrating away,
yeah,
crop failures from all these things that, way worse, especially, by the way, we're talking, I think you're being a little conservative. I think, should be looking at 3 degrees and later in the
yeah,
century. And that's, maybe not, survivable from a societal, not civil, not extinction point of view, but just civil society operating properly, and that just leads to war. But
yeah,
also, we're doing it now. We're doing this accidental SRM. It's killing 8 million people a year just from the pollution alone. No one says a word
yeah,
about that. That's
yeah,
pretty bad, and so it really, the funny thing is, I think what you're saying is when you do something intentionally versus
exactly.
just letting it happen. But I think in this case, the impacts of climate are so great that it's going to lead to conflict, even if it's, quote, not intentional, I guess. And is it
Yeah,
not intentional if we know it's going to happen and we choose not to do anything about it? I thought that's a
yeah,
philosophical question.
you could yeah, that's like a philosophical debate. Yeah, geoengineering is like, you are doing this thing to modify climate, and things like
Right.
pollution, you're not doing it to modify climate, you're doing it to produce energy. There's even, I mean, we're doing geoengineering even with things like, marine cloud brightening with ship tracks,
Right.
um, you know, modifying the amount of sunlight that has an impact on climate. So yeah, but
Yeah.
those are all kind of like indirect geoengineering.
Right.
So
Right.
actually, yeah. So in my mind,
Or
like
unintentional geoengineering.
unintentional geoengineering. So yeah, in
Right.
my mind, like going out to modify climate and causing damages is slightly different, but yeah, it's sort of a philosophical debate. We're certainly already modifying the climate a ton.
Well,
Yeah,
big time. I mean,
yeah,
so you're basically saying you think the hardest hit areas of the world. I mean, basically the poorer countries, the hotter countries are going to benefit, and then the northern latitudes in Canada and Russia might be negative. Although I guess they don't really have a lot of agriculture now, and this
yeah.
would
I
increase
mean,
because of the warmer temperatures. So you're sort of stopping something that might improve as opposed to
yeah,
stopping something that's there.
yeah. Like maybe they, if as it's warmer, they might, adapt and grow more, you know, more food there. And of course, I'm just talking about like plants, but there's other things you might care about, like permafrost loss, which is important in those places and stuff like that. I mean, in Arctic sea ice, maybe Russia. I think Russia might like less Arctic sea ice because it's lets them open up trading routes and stuff. But there's so many things to consider that. Yeah, I mean, I'm not. I wouldn't say with certainty like, oh yeah, these places are going to overall be damaged. It might, it depends on what they care about, I think.
And speaking of that, a little bit, did you take into account possible tipping points in your research? Like AMOC collapse would, especially in Europe, have a big effect on temperature in Europe, uh, s- especially Northern Europe. But actually, overall, it would diminish the warming that Europe is seeing or would see
Yeah,
otherwise. But I assume you didn't take that into account in your scenarios.
I mean, in in a lot of my crop modeling studies, like the crop model is implemented into an Earth system model. And so it has all of these things going on. It has AMOC collapse and stuff. I think for AMOC collapse, it is collapsing in the model in a lot of the scenarios. At least the climate model that I'm using, it collapses. But you don't really see big impacts over Europe for like a few hundred years. So if I'm just looking at like the end of this century, the impacts of AMOC collapse actually aren't that big. But yeah, how well models represent tipping
That's
points
the
and stuff is,
IPCC side. I think a lot of
yeah,
scientists now say we could reach the tipping point, which becomes inevitable around
yeah,
2050. But even then, it still takes 30 to 100 years
yes,
to actually reach its minimum point. But I think in
yeah,
that case, you still would see more impact in your models if your models were reflecting that. But
yeah,
so that's really interesting. Yeah, so it's interesting. You're worried about that it's on purpose, but overall, it sounds like overall, actually, SAI, well, again, doesn't hurt vegetation growth overall, number one, but when it comes to agriculture, it's not an overall negative thing. And it's positive in some places, maybe a little negative in some places, but it's not like, oh my God, we're dimming the sun. No one's going to be able to eat anymore.
no, I don't think so. I mean, I should say like all of this is still so uncertain. And
Hmm.
yeah, so you mentioned my like nutritional quality paper. So that was kind of a thing that I think no one had really in our field at least had never really thought of before. So like I said, the yield going up under SAI is probably true. How much of the crop you have. But there's things that are actually pretty important in a lot of places, like the quality of the crop. So how much? So my paper focused on how much protein is in the crop. Now, if you live in the U.S., you might go, well, who cares how much protein is in corn? That doesn't matter. I get my protein from meat or dairy or whatever.
Hmm.
But there's lots of places, like in Africa, that are malnourished, and they might get as much as 70% of their daily protein intake from corn.
Really?
And
Okay.
so, yeah, so I would argue that what happens to nutritional quality in those places is actually really important for them locally. And so I did
Yeah,
a
but does
study
that
where
take
I,
into account the reduction in calories? If I mean, again, we're talking about SRM versus not doing SRM. So we're talking about a hot, dry world, or and that's going to hurt plants,
mhm.
um, versus one that has these other conditions where maybe the protein goes down. But is that lower protein on a higher amount of food, do you think the food would be roughly the same too? I mean, the
Yes.
yield, the yield.
So that would be yeah. So in Africa, the yield is going to go up probably because you're reducing heat stress. So the thing that the nutritional quality would do, if you cared about that, is that if the yield goes up by 20% because you're reducing heat stress, but the nutritional quality goes down by 20%, then if you care about that, you'd have to eat more to get the same
Mm.
amount. So the net effect would be negligible rather than a
Right.
positive effect if you just looked at yield. So I'm not saying the nutritional quality is going to make it all of a sudden this damaging effect. You're still going to have probably a yield increase,
Hmm.
but it might be turning it from a really positive effect to maybe slightly less positive towards neutral effect. So
Okay.
I think it's something important to consider, especially for places that rely on these cereal crops for nutritional intake.
Well, it's really all fascinating. So tell us what's your current research? What are you working? What's some of your papers that'll be coming out soon?
So right now I'm focusing more on natural vegetation. So I mentioned forests. Most of my work in my PhD was looking at agriculture, but there's really been almost no studies that have looked at how radiation would impact forests. I mentioned there's observations from Pinatubo that suggest it would be a positive effect, but no modeling studies have really looked at how radiation impacts forests around the world. So I'm looking at that now. And one thing that's interesting, I'm writing a paper right now that I'm about to submit, is that yeah, the more diffuse light increases forest growth. That's something you'd kind of expect. But I'm using this new, sort of more sophisticated land surface model that actually represents canopy structure, whereas pretty much all land models used, in the IPCC and climate models and stuff, they represent vegetation really simply. It's basically just, one big leaf as like some fraction of the grid cell, which is clearly not. You can try to parameterize diffuse radiation and stuff, but it's not really the best way to do it. So now I'm using this model that has canopy structure, has tall trees, shading shorter trees. And what I actually found was that, yeah, the diffuse light is still a benefit, but now just reducing total radiation, so not even touching diffuse light, you would expect that would be a negative effect. You know, reducing sunlight reduces photosynthesis.
Whoop. Sorry about that.
You're still there.
Yeah, there was just a little, I don't know what
Okay.
happened there, but keep going.
So you would think that less total radiation would reduce photosynthesis. What I'm finding is that actually, you know, slightly less sunlight at the top of the canopy, like I said before, it's already really light saturated. It gets tons of sunlight. So slightly less actually really does almost nothing. And what you do at the same time, you're reducing the amount of sunlight you have. It's actually also reducing heat stress. It's reducing temperature at the top of the canopy, which tends to be the hottest part of the canopy. And so that's a feedback that actually ends up being more positive than the reduction in sunlight. And so I'm
Hmm.
finding that, you know, globally, the loss of sunlight for forests might actually be a good thing, which is kind of like not what you would expect, obviously. But mechanistically, I've kind of convinced myself that that makes a bit of sense. But it's still kind of theoretical. Like I'm using this model, but there is data, there is observation to suggest that that's true. You know, it's nonlinear like the diffuse light curve. You know, more sunlight is good. It's good. It's good, and then too much, all of a sudden, it starts to come back down, and it becomes damaging because you're just beaming the plant with light and heat. So it's kind of this thing that, again, you know, dimming sunlight, just doing that, you think, though, that would be bad for forests, but it might not actually be. You know, so I think that's evidence to show back from, you know, the Pinatubo paper that this radiation impact on forests is probably a pretty big benefit. So slightly dimming the
Great.
sun.
Great. Well, now I'd like to bring our co-mods in here to ask you some questions, and then we'll pick up some questions from the YouTube audience.
Sure.
So I'm going to invite, let's switch this way and invite Stacy in. And up, we got one of her cats lying there. Very good. We add
Yeah.
cats to try to increase viewership because
Yeah.
cat videos get a lot more
Mm.
views than climate videos. So we've tried to combine the two.
Yes, yes, we have to promote the cats. Yeah. Great to have you here, Brendan. This is super interesting. I learned today that corn has protein. I've been told forever it's a carb, and I didn't know that it had protein in it.
It has protein. I mean, for people in the US, we care. Yeah, it's like a source of carbohydrates, but yeah, it has protein too.
Okay, wow, I learned something new. And the I was very curious. I mean, this is so ridiculous, but you were talking a lot about diffuse lighting, and I was wondering, will we all look better with the diffuse lighting?
I don't think anyone's ever asked me that. That's a good question. Maybe, yeah. I mean, people talk
I
about
heard Well, I
it
heard the
would.
term often enough, and I know photographers do that all the time. And
I think maybe. I mean, if you do enough. I mean, people talk about, you know, this scattering of the sunlight would make the sky turn whiter, so the sky would look less blue. I think that's if you do a lot of it. It would make sunsets look nicer because you have more scattering and more, you know, make the sunsets prettier. But if it would make, yeah, your pictures, you know, make you look better, that's a good one. I haven't heard of that one before.
I yeah, I was thinking that combined with the sunsets, that we could probably get the photographers behind
Yeah.
this, you know. So it might be something to keep in your back
That's
pocket.
funny. Yeah, that's a good one.
Yeah. And I was wondering, are there, and apologies if you said this, but are there plants that do better under this? Like, or are there strains of plants? Like, I mean, I know GMOs is such a sore spot for many, but is there ways that we can help plants do better if they might not work as well with under the conditions?
That's a really good question. Yeah, there's different kinds of plants. So this gets more into like plant biology, but like there's different plants that have different photosynthesis pathways. So corn is a lot different than something like wheat. It does photosynthesis totally different. It's actually better adapted for like really hot, high intensity light conditions. So reducing sunlight might actually hurt corn more than something like wheat. But there's certainly different varieties of a certain crop. Like there's hundreds of varieties of corn and wheat. And there's different varieties that would be more tolerant to the light conditions from SAI versus ones that are used now, presumably. You could probably do genetic modification to maximize growth. I mean, there's people working on that for climate change, you know, making strains of crops that are best resilient to heat stress and stuff like that. So that's a really good point. I mean, that kind of stuff, you know, just complicates it even more, you know, but that's a very good point. There's all different kinds of varieties of crops that respond to things differently.
And I really appreciate you saying, because it's something I had never, you know, we've had so many discussions on SAI, but that the size of the what are they?
The
things.
aerosols, yeah, the little
aerosols,
droplets.
whatever.
Particles. Yeah.
That has that you can't necessarily guarantee what they're going to be because of atmospheric conditions. You can probably make a better guess, but the size matters.
This
that
is
right?
yeah, this is another great point. So I spend my time researching, putting sulfur dioxide into the stratosphere to make sulfuric acid droplets. That's basically what it is. And so these are liquid droplets that can sort of run into each other and coagulate and sort of make different sizes. And the reason that people study this is that that's what volcanoes do. We have a really good analog for that. But there's other people that say, no, the best thing would be to have solid particles that are engineered to be a specific size, and they're all one size, and you inject those and use that to reflect sunlight. So you would know what your radiative effects would be. And the downside with that is that impacts on things like, stratospheric ozone depletion, which we didn't really talk about, becomes way more uncertain once you just start putting random stuff into the stratosphere that's not usually there. We have no analog for something like, there's people that want to do like diamond dust or calcium carbonate, which don't go in the stratosphere. We have no idea what would happen to ozone, really. The uncertainty on that is much bigger. But for things like plants, knowing what the particle size would be from a solid particle would probably be really beneficial and reduce uncertainty for plants a lot. And so, yeah, this is a whole other thing. I don't know if you've talked about, there's this startup called Stardust. They want to do calcium carbonate particles. I was at a conference 2 weeks ago in Maine, and I was talking to them at dinner where I sat with them, and they're engineering calcium carbonate particles that are a certain size. They're going to put this coating on them to like make them repel each other so they don't, want to form together. But there's just huge amounts of uncertainty that come with that too. So there's, trade-offs on material type. It makes it even more complicated.
It's not like they're permanently suspended. They show up down here. So it's like, and then what happens when they do?
And that's another thing that people get really concerned about is because, with SO2, you're putting sulfuric acid in the stratosphere. It's going to come down on the surface. People who study that have found that that's actually probably not a huge concern. I mean, like Dan said, we're already putting so much sulfur dioxide into the stratosphere, and it's coming down really concentrated and causing acid rain. With SAI, it'd actually be really spread out, so it'd be a very small concentration. But there's places like in the Arctic that never see, this sulfuric acid that could be negatively impacted. So I think it needs more research. But
David Keith, David Keith was on the show, and he said that doing it in the stratosphere is 1,000 times safer because one, obviously we use a lot less than we're currently doing accidentally. Two, it falls out as rain typically, so we don't breathe it in. And three, 2/3 of it falls out over the oceans, not land.
Yeah.
Because it is spread out, as you said. So those factors all together, he said, makes it far, far more safe compared to what we're doing.
I do agree with him. I think that's not a concern, really, a major concern.
Let's go to Eli here for his question, then we'll go to the YouTube question. So, Eli, welcome.
Hey, so first a comment about the intensity. Actually, a lot of plants, and perhaps you could nag experimentalists to look at this specifically. What shaving off that little bit of peak intensity does under higher temperature and under vapor pressure deficit, if, for example, we do this at 2 degrees, because there are a lot of linearities in there. And in fact, another important variable is nighttime temperature. How cold does it get? Because all of those things will interact and will, along with how much fertilizer things are getting. Because, as you said, nutritional quality drops if you don't have enough nutrients, enough fertilizer to match the higher uptake. But you're also doing these other things which will also affect things. So I think that whole space has not been really well mapped out. I'm wondering, though, I understand that you're, for good reasons, focusing on stratospheric sulfate aerosol injection, but have you looked at all of the effects of either comparing to this, just doing it through albedo modification, or at the other extreme, doing it through space-based SRM, where you're not interacting with the atmosphere?
Yeah, so for other things besides doing stratospheric aerosol injection, I don't. So there's things like marine cloud brightening. There's things like cirrus cloud thinning. You could do albedo modification just by like painting rooftops white or whatever. I don't focus so much on the things that involve clouds. Clouds are so confusing and hard to model. Maybe probably more than plants, although both are kind of hard. So yeah, I focus mostly on stratospheric aerosol injection, but there's things like, there's things we know like with marine cloud brightening where, if you do it in certain places, like if you do marine cloud brightening in the South Atlantic, you turn the Amazon into a desert. So it's like there's certain places where you wouldn't want to do it, and how they kind of add up is still an open research question. With space-based mirrors, you wouldn't be getting that diffuse light benefit from doing that. So while I haven't looked too much at it, my understanding is that for plants, it would probably be, a slightly more negative effect, although you're also not getting the ozone depletion, which we didn't really talk about. You're depleting with stratospheric aerosol injection, you're depleting ozone in the stratosphere. So you might get, it's regionally dependent and depends on how you do it, but you might get more UV radiation reaching the surface. How UV radiation impacts plants is so uncertain. Even in, observational studies where you modify UV, it's like, even if you look at rice, there's hundreds of varieties of rice, and depending on the variety, it might like more UV or not like it. So that kind of stuff is really complicated. Depleting ozone in the stratosphere, you actually get less transport to the surface, so you get less surface ozone. That's actually a good thing for plants. Plants don't like ozone at the surface. So space-based mirrors are really interesting, and I'd like to research them more, but it's it's such an expensive intervention that I feel like that's more of a, if you were to do it, it would be a longer, down the road kind of thing. But
well, and we've had Ross Centers of
I know Ross
on here before, and he also agrees that I've looked at it, and I may be interested in getting involved in it, and that how far off it is seems to be largely based on extrapolating trends and looking at kind of like retail costs. But if you do it at that scale, you do it vertically integrated, and the costs are much less than that. And you could conceivably implement it much sooner. So I strongly encourage you to look into this. Thanks.
Yeah, that's a good point. Yeah, it is interesting. And there are some modeling studies that do just like solar dimming, which I've looked at a little bit, but I think it needs more research for vegetation impacts for sure.
Okay. Hey, let's move on to some. We have an interesting set of questions
yeah,
here. I see one right
questions
here, that one, probably the one you saw, Stacy. Question: How do nights with 40-degree plus temperatures affect plants' biological functions? How many nights in a row can trees or corn survive through? Because I assume you're using this sort of average temperature increase, but when you increase the averages a little bit, the extremes go up tremendously. And we're seeing that in Europe and things like that, things that we didn't think would happen for another 25 or 30 years. So what's your thoughts on overnight temperatures, extreme temperatures in general, heat waves?
Yeah, so all of the models that I use are taking as inputs usually daily average temperature, but nighttime temperatures are actually really important, especially for trees. Trees do most of their growing at night, which is what a lot of new research has actually shown. So nighttime temperatures are actually probably really, really important. And I would say that's probably just an open research question. I haven't spent much time looking at how nighttime temperatures are changing under SAI and how that would impact plants. But I think that's an interesting question that we should look at more. Yeah, because it's really important.
So in your tree study in Europe, for example, did your data include what's happening right now in Europe? 3 massive heat waves in a row that dried up all the soil moisture, this is something that wasn't thought would happen for another 50 years or something. It's happening right now. So do your data have that kind of scenario in it?
Well, the climate models, they're not forced with observations. They're just kind of running freely based on whatever, starting conditions you give it. So they simulate heat waves and stuff. How well they capture it is, I think they do a decent job. But things like this current heat wave, it might not be captured. It might not be having it this early on in the simulation. It's kind of just statistics. But yeah, certainly, heat waves are really important. It's also really important for things like mortality. So in my study, I didn't include mortality at all. I was just looking at growth, but we do know from observations that when trees stop growing, that's when they die. And so mortality would be really important to include too. And so this might even be a conservative estimate, if once you include mortality and the trees dying, because these heat waves are killing trees too,
Right.
which is really important as well. So yeah, those kinds of things are really important.
So I guess you're looking at that there's less carbon uptake because they're not growing as
They're not
much
growing
as we
as
thought.
much.
But if they stop growing, they die, and when they die, of course, they release
Even less,
their
yeah.
CO2.
Yeah.
So it's actually like way worse.
Yeah.
At that point.
Yeah, like these models really, most global models do not include mortality effects. That goes for agriculture too. And agriculture models are pretty bad at simulating extreme event impacts, especially things like flooding. Like climate models don't do that very well. So there's all of these things that the models aren't doing that great that we need to improve to get a better sense of the picture. Yeah.
And actually, I would like to call something to your attention on that topic. I dug into the question of soil carbon turnover and the biological component of that. And if you look at there's a particular ensemble, I don't remember the name of it. You look at the models within the ensemble, only one of them explicitly modeled a nitrogen cycle and a carbon cycle. And that was a nitrogen cycle and a phosphorus cycle.
Okay.
And that was kind of the outlier. And so some of these models are kind of janky. I just gotta say.
So I think at this point, all global land models have the nitrogen cycle and the carbon cycle, of course. None of them, I didn't even know one had the phosphorus cycle. Most of them don't have the phosphorus cycle. And there's a lot of observational studies coming out that show that phosphorus is actually really important at limiting growth of things like tropical rainforests and stuff. So that, yeah, if there's not enough phosphorus, then even if you cool things down and have high CO2, then the tree couldn't grow anymore. So I think including phosphorus is really important. Yeah, these models, they're simplified because they have to be. It's really hard to model vegetation globally, but they're certainly missing a lot of processes that could be really important. That would be interesting to look at, yeah.
Stacy, do you have another question for us?
Yeah. This from Nevitz at 1020 SRM and SAI. Is there a wavelength dependence in the diffusing the sunlight, and does it matter?
These are great questions. Yeah, so that's another good question. So these, when you do SAI, you're going to modify the wavelength and the spectrum of light, and these models don't account for that at all. I mean, they're just taking direct radiation, diffuse radiation, like watts per meter square. They don't account for wavelength at all. So that's another, I think, really important open question in the research is like, what is happening to the spectrum of light? We know that's important for plants. What is going to be the impact of that? No one's looked at that yet. So I don't have a good answer for that, but it would be important and good to look at.
Okay. Maybe we'll take one more, maybe, or.
Oh, just one more. Oh my God, how many?
I have one here.
Okay, you do one and I'll look.
Okay. What effect does heat have on plant cellular respiration? And at what point does that become a problem? Well, I guess it's heat in general just gets worse, but maybe you can just comment on
so when
heat impact on plants.
Yeah, so when heat goes up, the plants transpire more. Obviously, it's hotter, so it's just drawing more moisture out of the plant stomata. And so going back to the nutritional study, that was actually the mechanism that caused these reductions to nutritional quality under cooling. So when you have higher heat, you have more transpiration, and so more water is getting sucked out of the stomata, and that is being replaced by water through the soil and the roots, and that nitrogen is being uptake through the roots more. And so when you cool things down, you get less transpiration, you actually get less nitrogen uptake through the roots, and that's what caused the protein to go down.
Ah, okay.
So yeah, there's all these things going on. Yeah,
you want things to be simple. It's simple. Bad, but it's much more complicated
not
than
simple
that.
at all, no.
Wow. And also, as you increase CO2, the stomata close down, don't they? And isn't that the people just think that more CO2 is good, but isn't there a diminishing return on higher CO2?
Yeah, there is a diminishing return in the real world, and how well the models represent that, I'm not really sure. Like I said, when you run these models, you just increase CO2 forever. The stomata just stay open. They keep taking up that CO2 forever and keep growing more. So I think, I don't know how accurate that is to the real world. So yeah.
So
Cornell
one more
would seem
question,
like a
Stacey?
perfect. Yeah, there was Nevitz asked at 10:30, how did global COVID shutdown affect photosynthesis?
That's a good question. I don't know
It didn't. It decreased emissions by like 7%.
It did basically nothing to. I mean, atmospheric CO2 is like cumulative, so it's how much you put over time. So that would do nothing really for CO2. Pollution, it might have reduced pollution and reduced diffuse radiation. Maybe I don't know if anyone's really looked at that. I think
in India, it was very stark that it
Oh, really?
decreased aerosols, and that also affected temperatures regionally. So that might be an interesting thing.
That
for
is
you to look
interesting.
into.
That's a good. That would be
Certainly
a good analog. Yeah.
affected U.S. temperatures when we shut down all the airlines, and that was a noticeable effect that someone was smart enough to go check on when it happened. So, but yeah, so that's an interesting thing. But yeah, I wouldn't imagine on agriculture it would have that big an effect.
Regionally, yeah, like India, yeah, sure. I think it would have impacted it. Yeah.
So, Brendan, I want to thank you so much for coming on and telling us about this. This is an area where I think I think a lot of people just don't know what's going on. And if they know anything, they just either think CO2 good or they think heat bad. And it stops there. But
it's super nuanced. Yeah, plants are
very subtle, interactive set of things. And so it's important work you're doing, and it sounds like you are going to be busy for a while refining all of these models.
Forever. Yeah.
So when you have some new information for us, I'd like you to come back and tell us about it.
Sure. Yeah, that'd be great. Yeah.
But I want to thank everyone for joining us, and also to do what I forgot to do at the beginning is to remind everyone to please like and subscribe so that this program and others like it can reach more people, which is why we're here in the first place. So please help us with that, and also leaving a comment helps as well. So if you have your thoughts on climate change and agriculture, you leave them below, and maybe we'll have a chance to answer some of them later. And with that, thanks everyone for joining us, and we'll see you next time. Bye-bye. And thanks, Brendan.
Bye-bye.
Thank you.
Bye, everyone.